All right, good morning or good afternoon to everyone. I've had several requests for Reagan to be in a video, so here's Reagan. Say hello, Reagan. Say hello. Say nice to see you, everybody. Reagan, look at here. Look over here. Say hi to mommy students. Say hi. Okay, so that's Ray Ray. That's what we call her. Last time you met Rocky, this time you can meet Reagan, or Rocky's going to make an appearance too. Come here, Rocky. Okay, there you go. All right. She's not going to stay the whole time. She's going to have to go here in a minute, but thought I'd introduce you guys. This is who I'm with on Tuesdays and Thursdays. But if you guys could please get out your yellow notes packets from Chapter 10. We're going to be taking notes on the limiting reagent as well as percent yield. She doesn't want to do it either, but you got to do it. All right, I'm going to press pause and we'll return right after I hand her off to her dad. All right, be right back. Okay, no more baby. All right, so hopefully you guys are kind of shuffling papers here and getting out your notes. Yesterday we finished our stoichiometry notes, and today we are going to be taking notes on the limiting reagent and percent yield. Okay? All right. So this first slide talks to you about what a limiting reagent is. And believe it or not, you guys have already kind of learned what a limiting reagent is. You just didn't know what term or vocabulary term to use for it at the time. So think back to our chocolate chip muffin example from the beginning of this unit. Okay. In that activity, there was one or two problems about if you had not enough of one ingredient, could you still make the muffins? Okay. So for example, the recipe calls for 2 cups of flour, but one of the questions asked you, could you still make muffins if you only had 1 cup of flour? You could, you would just have to change the number of muffins you created, right? Because the amount of flour would limit how many muffins you could create or bake. Okay. In a chemical reaction, the same kind of idea can be applied. When 2 things react, so when 2 reactants react, one of those reactants will limit how much product you will get. And the reactant that limits how much product you get is called the limiting reagent, because it's going to limit how much product you get in the end result of your reaction. Okay. So we're going to go through an example together to kind of show you what a limiting reagent is and what it does in a chemical reaction. If we look at this particular reaction, it's the formation of ammonia from nitrogen gas and hydrogen gas. And in this particular reaction, you can see from the chemical equation as well as the models that there's 1 mole of nitrogen gas. Okay, that's right here. Ooh, yay. Let's back that truck up. Okay, so there's 1 mole of nitrogen gas and 3 moles of hydrogen gas that react together to form 2 moles of ammonia. Okay. However, the question at the bottom here asks you, what if we had 2 moles of nitrogen instead of 1? Okay. So in this new picture, we showed 2 moles of nitrogen reacting with 3 moles of hydrogen to get certain products. And now the products that we get, we still only get 2 moles of ammonia, but we have leftover nitrogen. So if you guys look, okay, on this side of our equation, we have 2 moles of nitrogen reacting with 3 moles of hydrogen. However, we still only get 2 moles of ammonia. Okay, and if you come back over to the reactant side, looking at the reactants, you can see why. Because even though you had enough nitrogen to make more ammonia, you still only had enough hydrogen to make 2 moles of ammonia. Okay, so in this particular example, hydrogen is your limiting reagent. And it's your limiting reagent because it limits how much product you can make. Nitrogen would be the opposite because we end up having extra nitrogen. So nitrogen is what we call an excess reagent in this particular example. It's left over. Okay? And you can see that up here in our picture as well because we had 2 moles of nitrogen left over after, or it should be 1 mole. That should a typo. That should be 1. But we have leftover nitrogen after the reaction occurs. Okay? So that's limiting reagent and excess reagent. All right. All right, so the next thing we'll take notes on is percent yield. Percent yield is a calculation that you guys are going to get some practice on either tomorrow or Monday when we do a lab. And percent yield is a comparison of how much product you get versus theoretically what you should have gotten. Okay, it's called actual yield or theoretical yield. You get your theoretical yield from the chemical equation. So when you go through the chemical equation and you use stoichiometry, you can calculate how much product you should get. Okay, you guys did a ton of that practice in the stoichiometry POGO. You went through and you calculated, you know, if I have 10 grams of the reactant, how much product should I get? That's called theoretical yield. However, theory is not often reality. Okay, so in theory, you might get 10 grams of product, but when you measure out your product after you do your reaction, maybe you only got 8.5 grams. Okay, so your theoretical yield comes from your balanced chemical equation and using stoichiometry to figure out how much product you should get. Actual yield is what you actually get in the experiment when you run through the reaction. Okay. Now, because these two numbers are different, there's a calculation that you can do called percent yield. And it's where you take your actual yield, and again, your actual yield is how much product you get from the actual experiment that you do, what you actually measure out at the end. Okay. And then you divide your actual yield by your theoretical yield. And actual yield is what you've actually measured out it's what you got from your experiment. Your theoretical yield is your calculated yield. Why is that not working? Your calculated yield from your equation. Okay. Now, some of you may be wondering, how come there's a difference? Why don't you always get your theoretical yield when you run an experiment? Because you technically should, right? According to the law of conservation of mass. However, at times in the laboratory, there can be some of the reactants that remain unreacted. Or you can lose some of the product in the transfer from one container to another. And for those two primary reasons, sometimes your actual yield or your measured product can be different from what you theoretically should get when you run the reaction. So because those two things can be different, there's a calculation to see how close your actual yield is to your theoretical yield, and that's your percent yield. Okay? Alrighty. That should be it. Let's double check to be sure. Okay, so then we just took our notes on percent yield, so this is going to be a quick example problem. So in this example problem, we have carbon monoxide combining with hydrogen gas to form methanol. Okay, you guys saw that example in your POGL yesterday. But in the lab, the above reaction was carried out and 76.32 grams of methanol was produced. However, when the chemist went through the stoichiometry, the theoretical yield should have been 84.68 grams. So they should have gotten 84.68 grams of methanol, but when they measured how much methanol they got at the end of their experiment, they only measured 76.32 grams of methanol. Okay, and again, as a reminder, that extra 8-ish grams, the difference between 76 and 84, that is likely due to some of the carbon monoxide or hydrogen gas not reacting. Okay. Another source of that error or that loss of mass could have been the transfer of the methanol. You could lose some of it when transferring it from one container to another to measure it. Okay. So when we go through and we calculate the percent yield of our experiment, we put our actual yield, so what we actually got, 76.32 grams of methanol, and then divide that by the theoretical yield. So what we should have gotten based on our balanced chemical equation and stoichiometry was 84.68 grams. Times that by 100, and then you get your percent yield. So we got 90.12% of what we should have gotten, which means we lost roughly 10% of our methanol somewhere. It either was unreacted reactant, we lost some of the methanol in the transfer, but that will happen, and so we need to have a percent yield to see how effective was our experiment, how much of our theoretical yield did we get, and that's what this number tells us. Okay? Alrighty, so that is it for notes for Unit 10. You guys are going to have some more practice doing stoichiometry that you'll spend the rest of the class time today doing. You need to finish it for tomorrow, and then tomorrow we are going to look at that together and correct it. So I hope you all have a wonderful day. I hope that stoichiometry practice goes well, and I will see you all tomorrow. See ya, see ya. Hit that like button.